In this session, we will control a soil moisture sensor, which looks like this, using CircuitPython, and we will use the analog A3 pin, just like last time. In this session, we are focusing on the Y12 pin, which is a critical component of our setup. To start, please take a 3-pin cable and carefully connect it to the Y12 pin, just as we have done in our previous sessions. It is important to ensure that the connection is secure to prevent any potential issues later on. Once you have successfully connected one end of the 3-pin cable to the Y12 pin, proceed to connect the other end to the designated port. This step is crucial for the proper functioning of the entire system. Additionally, we will be utilizing the OLED display to present important information. Therefore, it is necessary to connect the OLED display to the system. Make sure that the connections are firm and correct to ensure optimal performance. Alongside the OLED, we also need to connect the module, which plays a vital role in our setup. Once all these components are connected as described, we are ready to proceed with the next steps. In our previous session, we opened the code, and now, in this session, I will demonstrate how to erase the existing code and re-enter it with the new code specific to this session. This session's code is designed for Today's Ice Cream, Season 2, operating in mode 60 with our 864 iScanC address. The first step in the code is to clear the screen, which is followed by displaying the word soil. After that, we will use the analog input mode A3. The classification for this session is morning classification, which is very similar to what we did last time. This detailed approach ensures that you understand each step and the purpose behind it, allowing for a smooth and successful execution of the task. By following these instructions carefully, you will be able to complete the setup efficiently and without any complications. Remember, attention to detail is key in ensuring that everything functions as intended. Let's proceed with confidence and make sure that each connection is made accurately and securely. In this process, we begin by reading the analog input from pin A3 on our microcontroller. This input is crucial as it serves as the predicted sound signal that we are monitoring. The analog to digital converter, or ADC, plays a vital role here. It takes the analog signal from A3 and converts it into a digital value that our system can process. This conversion is essential for accurate sound prediction and analysis. Interestingly, during this particular instance, the ADC value remains constant, indicating a stable input signal. This stability can be attributed to the consistent environmental conditions or the lack of variation in the sound source. By maintaining a steady ADC value, we ensure that our predictions are reliable and that the system's performance is optimal. This process highlights the importance of both the hardware and software components working in harmony to achieve precise sound prediction. In this demonstration, we are working with a 16-bit display. As we did in our previous session, we are tasked with converting the ADC, analog to digital converter value, into a corresponding voltage reading. The ADC value we are dealing with translates to a voltage of 3.5 volts. Our goal is to accurately convert this value into a voltage measurement and ensure that it is displayed with precision, specifically up to the second decimal place. This process involves careful calculation and verification to ensure that the voltage reading is both accurate and reliable. By doing so, we can ensure that the data we present is both precise and easy to understand for further analysis or application in various scenarios. This step is crucial in maintaining the integrity of our measurements and ensuring that any subsequent data processing is based on accurate and reliable information. This is the next position we will be moving to, and it is crucial to understand its importance. We must ensure everyone is informed about the specifics and ready for the change. When the measured value falls below this specified threshold, it serves as an indication of dryness in the environment. For instance, values such as 60, 40, 50, and 51 suggest varying levels of moisture, with 51 indicating a moist condition, hence the red indicator. This observation is consistent with previous measurements, showing little to no variation from the last recorded data. Given that we are utilizing an analog to digital converter, ADC, in this process, it is prudent to store the data in its current form for future reference and analysis. This approach allows us to monitor changes over time and ensure accuracy in our assessments. Now, as you can see here, it displays the ADC value just like last time. And this is the converted voltage, but here it shows dry, indicating dryness. In this state, if you slightly submerge it, you can see it change to normal. You can also set and adjust the original wet range, but I set it too high, so it stays in the normal range. I think it would be better for you to modify the ranges for dryness, normal, and 2, moist, according to the environment you are using. This way, you can see it change from dry to normal based on the level of moisture. In this session, I use CircuitPython to control a soil moisture sensor. I will return with more content in the next session.